Pagano from Glasgow and Max Planck Bonn. This talk is now being recorded, and he will speak on the statistics of number fields, integral points, and Arakelov ray class groups.
Yeah, great. Okay, thank you so much for inviting me to speak at ZORP. And today I will discuss three questions, which at the beginning will look completely unrelated, but eventually I want to convince you that they are heavily linked. So the first question is counting number fields with a given Galois group. So K is a number field, G is a finite group. And then I want to ask the counting function of basically G extensions with counted by discriminant. So you take the number of extensions of K inside, say, some fixed separable closure, Galois, such that the Galois group of L over K is isomorphic as a group to G. And the norm down to Q of the absolute value of the norm of the discriminant L over K is less than X. And then you ask, the question is how many such extensions you have. So, okay, here there is a conjecture, which I believe was discussed also one of the last ZORP talks, Malle's conjecture in the strong form. Simon, is it big enough? Because previously you said.
Well, anybody who feels that the font is even bigger should speak up, but I think this is okay for me personally.
Okay, great. Okay, the strong form of Malle's conjecture is that there should exist a constant C depending on G and K, say, which should be a positive real number, which doesn't matter too much. And then basically it gives you a power of X depending only on the group, and the power of log X depending on the group and the base field. And I will, actually, let me put -1 here, and I will discuss these two numbers later. So that's the first question. The second question is you fix an integer n, which we will specialize a little bit later, and we simply ask how often is n a norm in the ring of integer of a varying real quadratic field to X. The third question is that you fix a number C, let's say a positive number, at least 2 actually, integer, and then you ask basically the behavior. What is the behavior? Behavior. And I will clarify what I mean by behavior. Here I'm being a little bit vague with behavior. I put quote, not because it's hard to explain what I mean, but just because I want, there are many questions you can ask, and I want sort of to say just one question that suggests all of them, of the reduction map from the unit group of a varying field into its reduction modulo the fixed place C. So basically you are asking the distribution of the fundamental unit of a quadratic field modulo C, like how often, for instance, the entire group, unit group reduces to ±1 modulo C. You can ask something like this. This, as you vary, here also square free, say, as you vary a real quadratic field. So these are the questions I'm going to discuss, and I'm going to discuss some new results on each of them. And also it will be clear at the end what is a common feature in all these three questions and how sometimes they do reduce to the same problem, which has something to do with this object, Arakelov Ray class group that is on the title. So that's the plan for today. Let me erase here. Let's start with this and see if it gets too messy. Then I'll use water. Okay, so let me start with Malle's conjecture, the first topic. This is part of the results I'm going to discuss are joint work with Peter Koymans that is upcoming. And we consider the case of G a nilpotent group, nilpotent finite group. Potent. Let me remind you what nilpotent means. There is a sequence that you can attach to a group which comes from successively taking commutators, so is defined by this recursion. The I plus 1 is commutator from G with the ith one, and G0 is G. And you say that a group is nilpotent, G is nilpotent in case this sequence collapses to the identity for J large enough. For J big enough, and this is actually equivalent. There is a different description that G is the product of a bunch of finite P groups. So it's the direct product of GIs such that GI is a prime power for each I. Okay, so for an nilpotent group, let me define a few quantities that will be helpful in telling you what these constants AG and BG were in Malle's. So L of G will be smallest prime factor of the cardinality of G. Okay, G is assumed non-trivial, otherwise there is not much to do. The set EG will be the subset of G consisting of elements of minima order. So different from G is non-trivial. Identity of order this number L of G. And yeah, I believe that is all I need.
Perhaps you're heading towards the smallest visible handwriting now, but
sorry, what did you say?
Maybe you could just write a little bit larger than that last line.
Ah, okay. So do you think I should capitalize a bit more this, like rewrite it, or?
I don't think you need to rewrite it, but if you could write just a little bit larger than that last line, that would be perfect.
Yeah. Okay. Great. I'll do that. Okay. So so recall that Malle's conjecture tells you that for any group we do focus on these groups, but for any finite group G, the counting function of the number of G extensions with bounded discriminant should go as a certain power of x. And times a certain power of log x. And our first result, so this is joint work with Peter Koymans, as I said, is that Malle's conjecture is actually correct for the following class of groups. So let G be nilpotent, with the set IG that is defined here be inside the center, which I denote by Z of G. So this is the center. Let K be a number field. okay, a number field. Then indeed you have that n g k x, the counting function that I defined in the first board, is indeed some constant depending on g and k. So all you need to know is this is a positive constant times. Let me now spell out what ag and bg are. So here I take L of g divided by the cardinality of g times L of g minus 1. You will see actually later why this is quite natural, times log x. Okay, here there is a little bit of a stranger expression that is the cardinality of Eg up to conjugation divided by the degree of a cyclotomic extension. Okay, this is probably too small now, I guess, but I can stop for a second and explain this power. So this is A of G, this is B, this number here is B of G, BGK, sorry. Okay, so the power here, in case it's not too visible, is the smallest prime factor L divided by the size of G times L minus 1, and here the power of log X is the cardinality of elements of minimal order, but only consider up to conjugation and divided out by the degree of a cyclotomic extension of precisely you have the Lth root. So this number could be 1 sometimes. And actually, this is an integer, and that's something that is not hard to prove. Okay, so there are 2 more results, and then I want to explain.
Carlo, I'm sorry.
Yeah.
People are asking in the chat if you could please write the exponents in theorem 1 separately, if possible. And
why not? Why not? Yeah.
Someone was asking if you could actually repeat the definition of IG. Someone else in the chat, like with bigger.
Oh, okay. So IG here is the number, is the set of elements of the groups that are that have multiplicative order precisely equal to the smallest prime factor. So suppose that your group has even order, then IG would be the number of involutions. So the number of elements whose square is the identity. So that is what IG is. And maybe let's okay. So maybe I was too ambitious. I wanted to put 2 more theorems in this board. Let's instead spell here AG. So AG is L of G divided by L of G minus 1 times the cardinality of G, and BGK. So, okay, it's the cardinality of this set that I just mentioned, but you have to take the set only up to conjugation. And then you divide out by the degree of the cyclotomic extension of K, where you add to K the Lth G primitive roots of unity. So you can always check, so this is the set IG modulo conjugation. You take the cardinality. You can prove that in this set, yeah, the cardinality of this set divided by already L of G minus 1 is an integer. So this in particular is always an integer. It's not hard to prove. So I hope that's big enough. And so if there are more complaints in the chat, let me know. Okay, so let me maybe, okay, that's theorem 1. Let me now erase theorem 1 and move to next 2 results. And then I will discuss a little bit how this fits into what is known. Okay, so basically for groups for which the elements of minimal order are inside the center, we can prove the asymptotic from Malle's conjecture for nilpotent groups. Maybe I should keep AG and BG here and the definition of nilpotent. And let me write theorem 2 and 3 on this topic. And okay, so theorem 2 is that under a slightly weaker assumption, namely when you ask that this set EG that plays such an important role in the constant in the power of log, is not central, but at least all the elements in IG commutes with each other, then we can prove at least the correct upper bound. So suppose, okay, still G is nilpotent, K a number field, and I always assume that G is implicitly non-trivial, otherwise these quantities are not defined, but it doesn't really matter. Then we can prove that indeed NGKX is smaller than some constant times x to the AG times, oh, sorry, and I forgot to say, I said it, but I didn't write it. IG consists of pairwise commuting elements. And there are actually many more groups like this than in theorem 1, then you get the correct upper bound, BGK minus 1, where AG and BGK are these numbers written here. So for these two classes of group, for the first one, we managed to get the full asymptotic, and for the groups where the elements of minimal order at least commute with each other, we gain the correct, we get the correct upper bound. And finally, we have a theorem where dropping this assumption, so any nilpotent group, we get an upper bound which is not quite of the correct order of magnitude in B. So we get for any nilpotent group and any number field, we get an upper bound with a B tilde. And B tilde, maybe I can define it here by saying that B tilde is the cardinality of this set where you remove conjugation. So basically, for any nilpotent group and any number field, we get an upper bound which sort of is like Malle's, except that the set here we fail to recognize a conjugation. When conjugation doesn't matter because the elements of minimal order are central, then this B tilde would be equal to B, and then this upper bound becomes an asymptotic. And when the two numbers are distinct, but at least the elements of minimal order commute with each other, then we can promote B tilde to B. Okay, so these are the three theorems, and let me tell you what was known about this. How do they?
There's a little conversation in the chat which some people might want to hear out loud, which is that well, Jordan and Alex and Peter have clarified that this is about counting Galois G extensions ordered by absolute value of discriminant.
Yeah,
it's not about counting degree n extensions with Galois group G.
No, indeed. So this is Malle. I said Malle in the beginning, but I should have said that this is Malle in the regular representation. So it's a special case actually of Malle. It's a special case of a special case of Malle because we are studying nilpotent groups, and in their regular representation, in other words, we are literally counting Galois extension with Galois group G. So maybe let me rewrite here indeed what was this. So this is L over K Galois inside the fixed separable closure with Galois group.
Unfortunately, you might have to write it a little larger.
Oh, sorry, what?
I'm afraid if you want to write the definition out again, you will need to write larger than that.
Okay. So maybe now that I am going to erase anyway, let me put it here. So this was L over K inside some separable closure, so Galois. with Galois group G, isomorphic to G, and the norm from K to Q, sorry, of the discriminant from L to K less than X. So this was the counting function, sorry, that I wrote previously. And indeed, so we are, it is, I think in the literature, this is called Malle's conjecture in the regular representation. There are, and indeed, yeah, that is what I wanted to say next. So those are the three theorems, and what was known before. So let me quickly recap what was known before telling you something about the proof. The previous results so the special case, so theorem 1 is about when the set it's for G nilpotent when IG is contained in the center. Observe that any abelian group satisfies this property. Any abelian group is nilpotent, and for sure, since it's equal to the center and abelian group, then any subset is contained in the center. So theorem 1 includes abelian G, which was a theorem of Wright. So this is from 89, right? And actually the proof that we give implicitly by sort of, if you follow the proof and you see which proof we give for this case is slightly different. So we get as a bonus also new slightly different proof. And right, I would say something about the proof in a moment. So for abelian G was a case of Malle that was known by this theorem of Wright. And it's now a special case of this. Let me quickly convince you that these groups can be much more complicated than abelian with this property. For instance, you might take the semi-direct product of a cyclic group of 2 to the n over the 2 to the n with z mod 4z acting on this by minus the identity. So if you do this, you will find out that the nilpotency class is huge. As n goes to infinity, the nilpotency class can become arbitrarily large, but this property remains intact. So there are many more examples like this. So this is these groups are in a precise sense, there are way more groups than abelians because their nilpotency class can be unbounded. So okay, that's the case of abelian groups. Another special case was generalized quaternions, which was done by Kluners. And let me say here that these are both special cases, but then there are many more results on Malle's in case you allow different representations. Maybe I will not give a list, but I will just say it orally. There are famous results by Bhargava about S4 and S5. There are results by Cohen, Diaz, and somebody else, and that about D4 inside S4, and recently Varma, Shankar, Wilson, and Altug, sorry, I didn't say it in alphabetical order, did it for when you order by conductor. So that is a rough list of what was known before. And actually that is about asymptotics. About upper bounds, let me say that, so this is theorem 3, that was giving an upper bound for all nilpotent groups. That there is a recent preprint of Kluners in 2020, which gives same AG, and the B tilde GK, which B tilde tilde for the special case of a certain group that I will write down here without commenting, is the group ring, is a semi-direct product of a group ring of a vector space over F2 act with the regular representation and with k equal q, can be actually 3 times, 4 times, differs at least by 4 with our constant, plus 4. So Kluners had a result recently that for some groups you lose in the power of logarithm 4 logarithm more. And that result of Kluners was improving previous work of Kluners and Wang, which was improving as well previous work of Kluners and Malle. Okay, so that is about the statement and sort of how it fits in what we know. And now I would like to say something about the proof. Before
I think Jordan has a couple of comments on what you were just saying. Maybe, do you want to unmute Jordan and say this yourself?
Yeah, no, I was just I was answering Armand's question in the chat about sort of, which is of course a big issue. I don't know if it's an issue in this talk, but about self-consistency and of Malle's conjecture. You know, if you take products of the groups, does it predict the thing it sort of has to predict? Which I think is yes for products of groups, but I wasn't. Yeah, there was just sort of some side chatter about.
Okay, thank you.
Okay, so yeah, maybe something that I didn't say also is that in the general form, Malle's conjecture has encountered some counterexamples, and there is an adjusted version of Malle's conjecture by Turkelly, though I must say that I think for nilpotent groups, it doesn't lead to any change for nilpotent groups, say, in the regular representation. And yeah, indeed, there are no known counterexamples of Malle in the nilpotent case. So what is new? What is new in our approach? New input. We give a parameterization, and I will explain parameterization. And I will explain in a moment what I mean by that. Of nilpotent extension of G extension for G nilpotent. Parameterization, which is very well suited for counting. And let me be more specific. We construct. Let me actually do it in a special case because it's rather a mess in the general case, but I want to explain one special case where the parameterization is as simple as one could desire. So let S be the set of square free integers. Then what we construct is a map PG, which depends on some choices that I'm not going to discuss. There is no time, from the power of the set S raised to the power the group G minus the identity. So basically these are, and I'm going to explain what prim here means. These are, this set here are vectors whose entries are square free numbers, and they are indexed by the group itself. And prim here means actually pairwise coprime. So it's not what usually people mean by primitive, pairwise coprime. And there is also something about negativity in this pairwise coprime that I'm not going to explain now. But it's basically, apart from the sign as well, there is simply they have no pairwise distinct prime factors into the set of G extensions, basically, which we parameterize by surjections from the absolute Galois group to G. So these are continuous epimorphisms, union a trash point. So some sort of bullet point So some vectors won't go actually into, oh, maybe this pairwise coprime is ridiculously small for the pairwise coprime. Yeah, so some vectors here won't make it to any G extension, and they will go to this sort of trash point. But some of them will go there. And indeed, the first property is that those that go here, they go bijectively. So these the properties are the following. If you restrict PG to the inverse the inverse image of this set here, PG inverse this epi GQG, which let me call prim SG minus the identity solve. This restricts to a bijection with a set of extensions. And there is a second property that you can read off almost entirely the discriminant from the vector. So the odd part, so if you have a vector BG, G different from the identity, such that BG is in the solve set, is in prim SG minus the identity solve, then you can read off the odd part of the discriminant from the vector with an easy formula. Then odd part, which I will denote by odd part of the discriminant, so the odd positive part, you take the absolute value also, discriminant of PG BG is going to be equal to the odd part of this product, G different from the identity, of DG to the cardinality of G to the 1 minus 1 over the order of G. So actually this power here explains AG. From this power here you understand AG quite well. And BG is really understood once you understand the structure of this subset of solvable vectors inside this set. Let me not explain how this is proved, how this is constructed, but only mention that it depends on a bunch of choices. One choice is the filtration, a filtration of your group G by successive central extensions. And another point, important point, is a choice of a minimal set of generators of the pronilpotent, maximal pronilpotent quotient of GQ, which comes from taking inertia elements at all the odd primes and then add 2 elements coming from ramification at 2. And using this group theoretic data, you construct this map. And from this map, the problem of the Malle problem becomes a problem here. And let me explain quickly in terms of this input, what do we do to prove the theorems? So that's the input. Well, then theorem 3 that by now you were probably forgot. So let me remind it. Remind the theorem was of the shape ng k x smaller than x a g log x b tilde, where b tilde is slightly worse, b tilde minus 1, slightly worse than the b from Malle. This theorem is simply count points, count simply integer, the cardinality of the set Vg you can now use this parameterization and forget the fact that you have to count solvable vectors, and you just take all vectors with the discriminant. So to say that the push forward of the discriminant function here, cardinality of G times 1 minus 1 over cardinality of the group generated by G. So G is not 1. Less than X. And if you count this, it is, so this is in prim. Let me not write the full thing. Prim S square. So these are square-free pairwise coprime integers whose product with these weights goes up to X. And then you find straight away this. So once you have the parameterization, theorem 3 is a complete triviality. Yeah, so what happens now in theorem 2? Theorem 2, you can actually, we can in this theorem sort of, let me say, promote B tilde GK to B. And to do that, we have to be, of course, a little bit more careful in counting here. We cannot just count all the primitive vectors. We have to count the solvable primitive vectors, and that is exactly how we pass from the wrong exponent to the correct exponent. And that is done by carefully analyzing local conditions coming from embedding problems that need to be solvable, local conditions at a prime P dividing an element of minimal order. And in this toy discussion, let me say that K is Q and G is a 2 group. Perhaps I didn't say it before, that is was meant to be. So G here is an involution. So all the elements in theorem 2, all the elements of the involutions in G are pairwise commuting, and there are local conditions in this parameterization to make sure that a point is in the solvable set. So maybe this is too small. Local conditions. These local conditions are solvability of certain embedding problems. And in this special case, under the assumption of theorem 2, we are able to prove that they are solvable with the expected probability. And indeed, let me say that we also have a heuristic for Malle in the nilpotent case. In terms of this parameterization, heuristically, we know exactly what you should prove in terms of local conditions at involutions to promote this B tilde to a B. The problem is that not always we are able to do that. So heuristically, we know what is going on. Let me phrase it like this, which was also one of our motivation, was to understand this mysterious exponent B in Malle's conjecture. In terms of this parameterization, this exponent, it becomes quite clear how it shows up, how the local conditions are creating that exponent. But the problem is that you are not always able to show that these local conditions coming from the embedding problems are solvable with the correct probability. And under this assumption, you manage. And let me say something about theorem 1. In theorem 1, in a sense, there are no conditions, there are no local conditions at involutions, at these variables to check. To check apart from a bunch of local conditions coming from G that is not an involution, and those are guaranteed from a bunch guaranteed by Shafarevich theorem. Guaranteed by Shafarevich. So Shafarevich has proved that actually for any solvable group you can realize solvable groups as as Galois groups over any number of fields, and nilpotent groups are in particular solvable. And that is the only input that is required to make the proof of, apart from the parameterization itself and basic counting, that's the only input required for the proof, at least in this special case of G a 2 group and K is Q. So let me now erase a bit more. Okay, so. Okay, so that is what I wanted to say about Malle, and I now what I want to explain is what to do next, basically. For instance, theorem 1 gives you the correct asymptotic for groups. Now we know. Let me. Theorem 1 covers groups like G is Z modulo 2 to the n Z, semi-direct with Z mod 4, where the action is by -1. But what to do? How about groups like G dihedral groups, 2 to the n Z, semi-direct with Z mod 2, where the action is by minus the identity. None of the theorems, apart from theorem 3, which doesn't give the correct, for this group doesn't give the correct power of log, none of these theorems really tells you how to do the asymptotic for such a group. So how about these groups? So it turns out that for such a group, for instance, and perhaps 4 groups, what you really need to do to go ahead is star. And star is a good understanding of Ray-class groups, the distribution of Ray-class groups of quadratic fields, C to infinity, C, say fixed, integer. And let me remind what sort of this object look like. It's a group that fits into an exact sequence like this. Okay, let me write it down. See, standard class group. So it's some sort of generalization of the class group, which plays an important role in class field theory. And you see already from this sequence that on the left there is exactly the group that was playing out in question 3, namely how does the unit group reduces modulo fixed integer, which you can think as a question of sort of weak approximation for integral point for like a conic, which you know already to have integral point, like x squared minus dy squared is plus minus 1. Well, it turns out that star is also the key to progress on topic 2 and 3. And in the time that is left, I would like to explain recent results on 2 and 3 and how sort of further progress on star is promising to give progress at the same time on Malle's conjecture and on questions coming from 2 and 3, actually more specifically 3. So that's the link, which sort of, the problems seem completely unrelated to each other. However, it turns out that to make progress on some special cases of the first one, you need to sort of do things that are also crucial to make progress on the other two problems. So they're linked by the method, if you like. Okay, so let me explain integral points in progress. This was problem 2. Yeah, the problem was asking if you fix an integer, how often it is the norm of an integral element in the ring of integers. So I fix the square free integer, and I take n the xy to be the norm form of the ring of integer, form of the ring of integer, O Q root D. I take notation R is either Z or Q. L is a prime or -1. And I define the set S R Lx to be the set of square free integers such that norm dxy L is equal to L, and I ask that L ramifies L, okay, ramifies. L divides D, sorry, chalk is so small, if L is different from -1. And then the question, of course, is for Q, this is a very classical topic to give a precise asymptotic formula for SQ LX. However, for Z, not much was known. And recently with Peter Koymans, oh, sorry, well, this is theorem 1, but different topic. We managed to prove that in case L is a prime, such that the absolute value is 3 mod 4, 4 and the prime, then the limit x infinity of the proportion of integers, square free integers that admit an integral solution divided by the one that admit a rational solution admits a limiting density. X exists and is equal to a certain number gamma, which I won't write down. It's an horrible constant, though having a very nice meaning. So it is a constant that is terrible to write down, but it could be explained with enough time quite nicely. So in case L is -1, unfortunately, we don't yet have a precise density result. However, we manage to improve upper and lower bound as follows: 0.543 plus 1. So we give upper and lower bound for the solvability that slightly improve the previously known bounds, SQ minus 1x 0.59. Too much plus middle of 1. The previous results on these topics were due to Fouvry and Klooners, and later Klooners managed to obtain upper and lower bound. Here there was a 2/3, and here there was a slightly a smaller number, 0.4 something, 194. And this was improved sometime before this result by Chan, Koymans, Milovic, myself, where this was improved to 0.53823 something. And yeah, so that is what I want. The results I wanted to present about this topic, and the connection with the distribution of Ray class groups is that, let me not write it down exactly, let me just say it orally, is that to control whether this equation has a solution, you basically, let me actually contradict myself and say something, need to control basically the distribution of the two infinity parts of a suitable narrow class group together with the behavior of the ideal above L in there. So you need a control distribution of this. And by that, I mean something quite specific, which I'm not going to write down. And the behavior of L there, I mean statements like how often L is actually a 2 to the k power for some k, for any fixed integer k. And it turns out that if you are actually able to do this for all k, then you would get the exact density. And sort of playing out with more and more k, you can improve lower and upper bounds more and more. So you see how sort of the distribution of Ray class group together with some data in it, it's at the root of progress on this question, just as on the previous topic. And I want to conclude saying something about question 3 in the remaining 3 or 4 minutes. And sort of what is hopefully going to happen next. So this is more on integral points, part 3. Let me just state a theorem. I think I don't have time to say anything else. This is a joint work with Alex Bartel. This is a special case of what we actually do, but for simplicity, let me state this. So I take a prime that is 3 mod 4, and I take the family of real quadratic fields inside the family of real quadratic fields K with C inert, then the proportion, the probability, when you order things by, in the sense of the natural density, when you order things by the size of discriminant, the probability of the event that the sides of the class group is odd, of the double of the class group is odd, and the fundamental unit generates up to odd powers. So this is what I'm going to write here next. So in symbols, OK, odd C generates as much as it can, squares 2 tensor Z2. Is generated by a fundamental unit. Generated by, so the probability of this event, OK star, so exists and equals one of these products that you often see in the Cohen-Lenstra setup, the product of 1 minus 1 over 2 to the I, from 1 to infinity. And I see that I don't have time left, but what I want to say is that this theorem comes from understanding indeed the distribution of a slightly more mysterious group, Arakelov-Ray-class group, that is a compact group whose group of connected component is the classical Ray-class group. And it turns out that to make progress on this type of questions, namely weak approximation for conics, basically, for a conic that you know to have integral points, but you want to know how do they go modulo C, it is basically crucial to understand the distribution of the two parts of the Arakelov Ray-class group, and that it's as well as you saw at the beginning. So we expected progress on this topic will at the same time give you progress on Malle's conjecture and on the problem of weak approximation for integral points in conics. So these problems that at the beginning seemed completely unrelated are partially part of the same program, basically. And that is perhaps a good point where to stop.
Well, thank you very much. So let's take a moment to unmute our microphones and have a round of applause for our speaker.